I'm going to stop here and remind you, I don't know if I gave it to you last time, there's a problem set for Chapter 6 that I'd like you to do. That would be Chapter 6, do problem 6.2, 6.4, 6.6, and 6.8. And those will have to do a cyclic voltammetry. Well, what's the difference? Well, cyclic voltammetry, I think as we've mentioned, uses a ramp up and then a ramp back to some other potential. And maybe perhaps back to the initial potential, perhaps back to some other potential. And in fact, you can imagine that the wave shape in cyclic voltammetry could be quite different. You might have a wave like this where you have a different forward and reverse, and maybe stops, goes to some different potential and back, pretty much anything you want. The theory that we develop usually only applies for simple waves like this, although we can do simulations for any arbitrary linear sweep in potential. Well, we do a sweep like a potential sweep like this. This is the current versus time. I guess we have to go to the next page. And we observe a current versus time shape. And if we look down that thing, we see for the first part of that curve, it's just the same as a linear sweep. So we'd see the same exact curve as before. But on the reverse, then we see a different shape. What's happening now? Well, if we think about what's happening, during the linear sweep voltammogram, we're sweeping through the redox potential of our material. So we're, say, reducing an oxidized species. It's being reduced, so we're seeing some current flow. At some point along this curve, depending on how far out we sweep with potential, the concentration at the electrode surface will effectively be zero, just like in the Cottrell case. If we go sufficiently negative, all the concentration of species O will be used up. The rate of electron transfer is sufficiently fast to make that happen. So even if it's relatively slow kinetics, we're still going to see a peak when that, about the time when we've got zero concentration of O at the electrode surface. At that point, we're making a lot of R near the electrode surface. And so when we sweep back, we're going to see a curve and then a reverse peak. Actually, a little bit more like that. And that sort of wave. Again, we typically would plot those versus potential. And we get a familiar looking curve for electrochemists. This nice, what they call duck-shaped curve, with you get a duck in the bill. Depending on how you can go out farther or shorter, and you'd see a different sort of waves. Well, let's analyze that peak. Let's look at the things, how we would call some of the features of it. First of all, most of the features are exactly the same as the linear sweep behavior. For example, we would have a potential for cathodic process, we'd call it EPC, and we would have an IPC, the current at that particular point. What about on the reverse sweep? Well, if you think about this experiment, remember we're making the concentration of O essentially zero at this point. So any potential farther than this time, as long as we're negative of the E0 of the process, is essentially equivalent to the Cottrell type experiment. And remember in the Cottrell type experiment what happened when we did a potential step out to some point. If we think about our curve when we're stepping out here, we get a t to the 1/2, t to the minus 1/2 response. So this curve here is like the Cottrell curve in that sense. It gives us a minus t to the 1/2 curve, and you can see it better in this I versus t plot. And even if we've wrapped it around, it's still decaying with that t to the minus 1/2 behavior. So here we have IPC. What about IPA? What's the peak current for the reverse wave? Well, we could think about it being this particular current, but that's not really the correct amount. That's just the current below zero. What we really want is to measure from the baseline, and the baseline turns out to be this t to the minus 1/2 decay. So if we draw a little bit of a curve there, often a straight line, but you could be fancy and draw it as a t to the minus 1/2 line. Here now we see the true IPA value, which is measured versus that extrapolated baseline from the peak. And the ratio of IPC over IPA is approximately equal to 1. It should be exactly equal to 1 for equal diffusion coefficients and for situations in which we have no kinetics are reasonably fast, basically quasi-reversible kinetics, and we don't have any chemical reactions occurring at the same time. If we just do the same curve, but we'll say let's sweep out a little bit farther. Oops, that's not a very good one. Let's try that again. Say we swept out to a farther potential. Same procedure as before. We would just extrapolate that baseline like so, and you can see now that the IPA would be a little bit less, but in fact the ratio is still the same. These are still equal to 1. So that's a pretty good diagnostic. It's not a very accurate one because we have to draw this little baseline. It's not very clear exactly where you should draw it. There's some procedures people have published in that purport to give you a very accurate baseline, but a lot of computer programs now for doing voltammetry that are commercial will give you a routine that will automatically draw that baseline. And this only works when you have really nice looking voltammograms like this. Often you don't have really nice looking voltammograms like this, and then it's really tricky figuring out where to draw that reverse line. There is another important number though in cyclic voltammetry. Most of the things are the same as the linear sweep voltammetry, the EP1/2, the EP/2 value. So those are all the same. What you often want to know though is EPA minus EPC, and that's what they call the delta E peak value. That's the potential difference between those two peaks. Notice they're not lined up one over the other. The reason is there's a diffusional component to this, and so that diffusional overpotential gives rise to that separation in peaks. And it turns out that it's about 59 over n millivolts at 25 degrees C, and that's a number you should keep in your head if you're doing CVs. You expect that 59 millivolt peak separation for reversible voltammograms. Again, if we see a shift away from 59 millivolts, that suggests a couple things. One is that we've got kinetics, slow kinetics, or the fact that we may have a situation in which we have some ohmic drop or IR drop. There is a slight dependence on this value as to when we do the reverse sweep. Notice here we've gone to farther potentials, and that particular point on our curve is actually used, they use the term E lambda for that. And it turns out you have to sweep out a little bit past the peak to get this 59 millivolts. If you sweep back just right at the peak or a few millivolts beyond it, you don't get 59 millivolts on the peak separation. It's a little bit different. But most of the time you do sweep out 100 millivolts or so, and then that you do get the 59 millivolts. Okay. The other one is if you take the average of the two peak potentials, that's what they call E1/2, and that has a similar connotations as we had with linear sweep voltammetry. All right. What I thought we'd do is take a look now at a simulation of the cyclic voltammogram. We can look very clearly at the diffusional processes that are going on when we actually do a voltammogram. And this is one, again, I would suggest that you download and use yourself, and you can examine some of these things. Let's see. Now this one here I'm going to show you is a nice Windows version. That's kind of a toy in one sense. It really doesn't help you do any research sort of things, but it does help you help you understand voltammetry a little bit better. And so what we have here is two windows, and up at the top, here and here are dimensionless potentials. And if you look under About, you'll see what those are. These are just the potentials minus the 0 times NF over RT. So these are dimensionless parameters, and so it doesn't really matter what those values are. Lambda is the dimensionless rate constant, and you can see there's K0, diffusion coefficients, alpha is here, scan rate is in this particular lambda, just the same as we wrote in the notes the previous day. And if lambda becomes large, that suggests that K0 is large, or perhaps the scan rate is small, or the temperature is large. All right? And alpha is a transfer coefficient as before. So lambda, making lambda very large like I've got here at 1,000,000 is equivalent to a reversible voltammetry. Alpha 0.5 minus 10 to plus 10, that's about 250 millivolts on either side. And so let's start our voltammogram. What we see down at the bottom graph here is a plot from CSI to CSF and then back again. And so here we see the voltammogram you would see if you plotted current versus potential. And for completeness sake, we actually have sort of a time record here. And so this would be the current versus time. And you can see the shape of our voltammogram like so. And so that gives you the shape of the voltammogram. You can see if we change the kinetics to slower and do the same thing, now the peaks are shifted out. In fact, we don't really even see a peak hardly in that particular case. We could make the limits a little larger, and we'd see them now. Again, the forward wave is exactly the same as you'd see for linear sweep voltammograms, but here you see the wave there. Now that would be a slow quasi-reversible, nearly what you'd call irreversible wave at this particular point. But let's go back to the rapid rate constant, and let's redo the, let's actually stop this and make our, back to the original things. Now, as we look above this curve in this region here, what we have is at any particular time in the simulation, we're looking from the electrode surface out into solution. So at this particular point in time, this column up would be the concentration profile in solution. And we've got a color-coded map to indicate that concentration. So as you see, this would be the concentration of species O out from the electrode surface. And for most of the time, O is going to be, up to this point, especially out in the bulk, it's nearly 100%, only very slightly affected by diffusion. As we start to get into a potential where reactions can start occurring, the electrochemical process converts O to R. Some of the O is used up near the electrode surface, and we start to see a diffusional gradient. And this color coding indicates that. And you go from, say, 100 to 90% of O right at this particular point, and so you're seeing this initial exponential rise in current as you'd expect for the current potential relationship from the Butler-Volmer equation. Now right at E1/2, at this dashed line, we'd expect the Nernstian conditions to hold, and if we're at the E1/2, we're going to be at essentially at E0, and at E0, the Nernst equation would suggest that the concentration of O and R is equal to each other at the electrode surface. And so if we look up that dashed line, you can see right at this region between at 50% is right here, and that's what we see, a 50% O and R ratio. 50% of O is there, so that suggests 50% R. Now as we go past this point, and just beyond the peak now, what you see is that the concentration of R is close to 0. We just use yellow for 0 to 10%. So it's not exactly 0 here, but it's pretty close to it. And then you can see it's 0 for as we go down this point, along this point. And this would give us that t to the minus 1/2 behavior as we'd expect. And if we're going out from, say, this point, we can see that diffusion is now occurring, and we're seeing diffusion away from the electrode surface and up the concentration gradient, and you go from 0 to the various values. Now, what happens now on the reverse sweep? Again, you see that nothing is really happening. In fact, it's as if we have not done anything to the electrode other than continue to make O, or to make R from the O species, oxidized species. Because at this point, nothing is happening. However, as soon as we get to this particular potential on the reverse sweep, which would be about over here on the actual CV curve, you can see now we're starting to convert the R back to O because the potential is sufficiently positive now to do that. So R is going back to O. So quickly we chew up all the R that's near the electrode surface, which means that we're regenerating O near the electrode surface. And again, at the E1/2 point, we're seeing at 50% level. And then as we sweep more and more positive, the concentration of O returns to 100% near the electrode surface. Notice, however, that it doesn't return to 100% in the bulk solution. And even after we go back to the initial potential, there's still a bubble of perturbed concentration of species near the electrode surface, and that suggests that we don't have the same conditions right at the end of the scan as we did at the beginning of the scan. In order to regain our experimental conditions from the beginning, we'd have to do a couple things. One is we could wait a long time for diffusion to disperse this little bubble of material, or we could stir the solution, and that would regain a bulk concentration. Just for you guys doing voltammetry, the rule of thumb is usually you want to wait 10 times the length of time of the CV. So if the CV takes 10 seconds to do a scan, you want to wait about 100 seconds to do the next scan. Or you want to stir well between those 2 times. And so that's a good rule of thumb for making sure you're not, because if you do another CV right away, you won't get the same behaviors you'd expect from the first way. Let's just try that. Let's go to 2 scans in a row, and we'll see what happens. We see the first scan, same as before. Again, this is reversible voltammetry. We get the way back, and now we're going to start another scan. And you see that bubble of material is in the solution nearby. And so that perturbs the response. And notice the second wave doesn't start at 0, it starts below here. And the peak current is not the same on either one, and a lot of it is different. Not substantially different, but pretty close to different. Different enough that the theory would not be exactly correct under those 2 conditions. And here's again why you can see we're not go to 0 on the reverse sweep, because we haven't regained the original diffusional conditions as before. And if we do a number of sweeps, let's do 10. I want to point out, if you look at, say, this line, this 90 to 80 boundary, let's watch it as it sweeps again. What you'll see is that 90 to 80 boundary has moved way up here, but even these other boundaries are now moving out. And so that essentially that bubble of solution becomes more and more prominent away from the electrode surface. And that's why we're getting these curves, which will now, after a certain number of cycles, begin to resemble each other, and we essentially don't see any particular difference. After, say, 10 or so sweeps, we get essentially the same curve over and over again, if a couple things are true. One is that we're not stirring the solution somehow by vibration, and B, that we're not undergoing any other chemical kinetics effects. So in other words, R is not being chewed on with some chemical process. And we'll see what happens when we have chemical kinetics a little bit later. But this final wave that's occurring after a number of sweeps is also called a steady-state voltammogram. It's a little confusing, but it's referred to as steady-state voltammogram because although it does change with time, it doesn't change with continued sweeps. And that's what they mean by steady state. So it's not a time independent so much as it's a sweep independent, number of sweep independent things. Now this particular curve is based on dimensionless parameters, and so you don't see a change in we don't have a number in here to put for sweep rate or things like that, and so on, but because that's all dimensionless quantities in this particular curve. All right, well that's a reversible case. Let's take a look at what happens when we go to quasi-reversible kinetics. So let's go back to our notes briefly. Okay, now in quasi-reversible kinetics, what do we expect to happen? Well, remember in quasi-reversible case, we're not having rapid kinetics, so we don't expect equilibrium to occur rapidly. In other words, if we're doing a sweep of the potential, we don't expect equilibrium conditions to be maintained at the electrode at all times. That generally causes an additional overpotential to be manifested itself in the curve. And so instead of a curve like this for a reversible case with a nice 59 millivolts peak separation under quasi-reversible conditions, the peaks will shift out, and you'll see an increased delta E peak. So this is a very diagnostic number. You can look at the delta E peak value, and if you see a shift away from 59 millivolts, that suggests quasi-reversible kinetics. Again, alpha has a similar type of effect. If we go to alphas of more than 0.5, remember the effect. The alpha of more than 0.5 tends to sharpen up the cathodic process. So we would see, let's draw our quasi-reversible for alphas. 0.5 would be something like that. If alpha was, let's say 0.7, we'd see a curve more like that with a sharp cathodic wave and a broad anodic wave. Let's take a look at that on our cyclic voltammetry simulation, and we'll see how that works out. Let's go back to the computer screen for a second. Let's make K0 slow by making lambda small. Now we've dropped the K0 down, lambda down to a small value, not really small. It's hard to tell exactly what the delta E peak is here, but notice particularly at E1/2, at the E0 for this particular redox couple OR, we no longer see that 50-50 O&R ratio. That 50-50 O&R ratio has shifted significantly more negative. And that's, again, an indication that we no longer can maintain equilibrium conditions under these slow kinetic situations. And notice the shape of our diffusional process is less. We don't see as much of this yellow because we don't have as much time to make R under those conditions. Let's pop alpha up to a 0.7, and if you'll have to kind of try to remember the shape of that wave. Let's take a look at what happens when we have 0.7. You can see initially that peak up is much sharper, and the reverse wave very much broadened, and that's again an indication of alpha 0.7. If we go to lower alphas, 0.3, this wave should be broadened, and the reverse wave should be much sharper. And you can see that clearly there. And the waves look quite odd, actually, at this point. So again, even small changes in alpha are quite easy to spot when you have slow kinetics and with cyclic voltammograms. And that's, again, one of the advantages of CV is you can visually observe some of these effects indicate to yourself that, okay, there's something wrong with that, let's look at it more closely and then determine exactly what those values are. And we can continue to decrease lambda if we do so. Lambda will now be in a situation where essentially we have quasi-reversible kinetics. And notice I changed the final potential out to 19.7, and that initial curve is you don't get any peak. We haven't got to the peak yet, and this is kind of like a the initial wave that you'd see on a sigmoid, but it doesn't. We haven't completed it. Let's increase the value out a little bit more. Go to 30. And we eventually do see a peak. But we don't see any reverse wave at that point because the kinetics are slow, and so we don't see a reverse wave. If we continue, if we made the other sweep far enough back, we could probably see a reverse wave, although I'm not sure we will. Okay, yeah, we do. And you see that's a pretty irreversible wave. It's irreversible not because it doesn't reverse, but the fact that it takes a large overpotential to do that reduction. And effectively, the rate constants, or the KF here are the only ones we have to worry about. The backward rate constants are always so slow that they're negligible. Notice the other effect when we have this sort of irreversible kinetics. This bubble of material has plenty of time to dissipate. Notice what happens when we do irreversible kinetics. Even though we're beyond the point where we can make O here, once we sweep back, now we're not only not making R from the O, but we're not chewing up the R by converting it back to O. So all we're doing here at this point in the wave is a simple diffusional process. We've got a diffusional amount here, and it's just diffusing away from the electrode surface. And until we get to this potential here, now eventually we see a return again of that R back to O. And so notice the peak heights are not 1, and that's because some of the material has now been able to escape the region of the electrode surface, and that causes the ratio of IPA to IPC to be less than 1. Now, again, I want to re-emphasize the fact that these are only electrochemical kinetic situations. Now, when we have chemical processes occurring at the same time, things can get quite confusing, and it'd be hard to tell the difference sometimes between an electrochemical kinetics problem and a chemical kinetics problem. If we go back to our original situation here, and we did a sweep like this, we might be confused initially and say to ourselves, you know, we're not seeing a reverse wave for the reoxidation of R here. It should be here, but it's not there. Why is it not there? Well, there's only two real things to think about. One is that the electron transfer rate is very slow, or R is participating in a chemical reaction in which it's being chewed up. So there's no R to be oxidized. And so it's hard to tell just from looking at that particular wave which of the two things are true. And we'll see a little bit later how we can use varying scan rates and other things to be able to distinguish between an electrochemical irreversibility and a chemical irreversibility. All right. Now, one other thing I want to talk about, although it's a little bit advanced, but I want to bring it up because we see this a lot in voltammetry. In fact, it's more the rule than the exception, is that we have more than one electron transfer process that can possibly occur, especially for biological molecules or organic reactions. Often what we see is a 2-electron process instead of just a 1-electron process. Many inorganic processes are just a 1-electron reaction, and some organic reactions are the same way, but many organic reactions and almost every biochemical process is at least a 2-electron process. So let's talk about multi-component reactions in voltammetry. N is greater than 1. There's actually a number of cases. One case is this case where we have two molecules, O and O prime, and O prime E0 is more negative than O prime, O, regular O. In other words, we're having a reduction process that's occurring at a more negative potential. In that case, what you'd see are curves that look something like this, where here would be the O to R. And then if we have a second component and we keep sweeping, we would just have an additional wave that would be essentially placed on top, a linear combination of the two currents, and you'd see O prime to R. So you'd see waves something like that. It would just be a linear combination of those two waves. Now the key to this sort of behavior is that O and O prime are non-interacting. In other words, they're not linked through a chemical reaction process. They're not linked by a homogeneous electron transfer process. In other words, once I make species R, it doesn't react with species O prime, and vice versa. And in this particular case, where O prime is more negative E0 than the O, we don't have to worry about that. And so that's always the case, and it always works out if we have two different redox couples that are both oxidized. We're going to see waves like this, and they might be closer together, they might be farther apart, and so on. O prime might be, is always going to be the one a little bit farther. However, the other more interesting case is where we have a situation like this. We have ox to red at some E0, and then red can be additionally reduced. Let's call it red prime at some other E0. Now in this case, there is a direct linkage between those two molecules. Now sometimes there might be a chemical step interposed here or something like that, and we can think about the simplest case would be this one here, simplest to think about. If E02 much more negative than E01, essentially we get the same type of curves as we saw previously. We'd see two separate waves. I'm not drawing these very well, but let's try that again. Waves like so. And again, this would be ox to red, and this would be red to red prime. What happens when E01 is much more positive, or E02 is much more positive than E01? Well, now we have an interesting situation, because once we've made red, it's has enough it has the potential at which it can actually interact with red prime and regenerate ox in this species. So what you see is effectively the same as what you'd see for a 2-electron process. In other words, you'd see an n equal 2 wave with the proper peak height. Remember, that's an n to the 3/2 dependence for n. Okay, and that would be, that's often the case, especially for those organic situations in biological systems. You make a reduced molecule that actually can be reduced at a much easier potential than the parent electrode. So in other words, we make this, and it requires a significant amount of potential to make that. But then once we've made it, it turns out it's much easier to reduce this again, and so the potential of the electrode is already at the potential required to reduce this. So we don't need any more potential, it's already there, and so that immediately proceeds to red prime. And the potential that you observe is actually the average potential for those two molecules, for the two E0s. So E0 net is equal to E01 plus E02 over 2. Whereas this would be E01 that'd be E02. All right. Interesting case happens when the two E0s are close in potentials. E01 minus E02 is less than about minus 100 millivolts. Now the potential of those two is sufficient that we're not at a potential when we do the one, so that the amount immediately gets reduced. And we also have some significant kinetic ability for one molecule to reduce or oxidize the other molecule. And what you see is a broadened wave, and it doesn't look really like a 1-electron wave or even a 2-electron wave. Okay. Well, we'll consider these things again when we talk about chemical processes, and we'll see the effect of this chemical process on these multi-component reactions later. But I want to give you that idea right now. All right. How are we doing on time?